Hello, ladies and gentlemen. Today we're going to continue our conversation about functions, and specifically, we're going to look at the notation that we use when we are dealing with functions. If this notation is used, it is helpful because it helps us to understand and communicate that we have determined that that equation or graph or table is in fact a function. Function notation is also helpful because it allows us to communicate mathematically without using a lot of words. So it might take us a full sentence to write out without function notation. When we are using function notation, we can express using some quick symbols. Okay, so let's get started. We're going to begin by looking at some of the very commonplace notation that you should become very familiar with. This right here is the basis for function notation. Okay? It is read f of x. So when I see this, f parentheses x, I want to read it f of x. Now it is commonplace that when we see a variable and then parentheses, that we would want to think that those are multiplying. But that is in fact not the case. When I see this, f of x is actually representing my output. It's like a fancy way of saying y equals. So instead of saying y equals, for example, 2x plus 5, I could say f of x equals 2x plus 5. F of x, then, is the output, and x, what's inside the parentheses, is the input. Okay, let's get started and look at some actual examples, and hopefully this will start to make a little bit more sense. This says, since functions are rules that convert inputs, typically x values, into outputs, typically y values, it makes sense that they must have their own notation to indicate what the rule is, what the input is, and what the output is. For each of the following functions, find the outputs for the given inputs. Okay, so the first function rule that we're looking at says f of x is equal to 3x plus 7. Okay, we are asked to evaluate two different questions for letter A. We're asked to evaluate f of 2 and f of negative 3. So what this is telling us is that whatever's inside the parentheses is our x value. So instead of saying f of x, we say f of 2. That means that wherever we see an x in the function rule, we are replacing it with the number 2. So instead of 3x plus 7 right here, we're going to write 3 times 2 plus 7. And 3 times 2 plus 7 is 13. So f of 2 is equal to 13. Now as I look at this, like I said, 2 was my input, 13 is my output. Okay, let's try the next one. F of negative 3. Now negative 3 is my x value. That's my input. So I take the rule, 3x plus 7, and I replace the x with a negative 3. So 3 times negative 3 plus 7. So f of negative 3 is equal to, see that's negative 9 plus 7 would be negative 2. So again, looking at this, negative 3 was the input, negative 2 is the output. Okay, now we have another function rule. You'll notice that we're using a different letter to introduce the next function, whereas in the first one we used f of x. This next one is h of x. So you can use any letter in front of the x. The first one would have been called function f. This one is function h. So generally f, g, and h are the most popular function names, but we can use anything. Okay, so we have h of x equals the square root of 2x plus 1. So that's our function rule, and now we have to evaluate two different outputs based upon inputs. So the first one is h of 4, where 4 is our x value input. So we're going to take this function rule, and wherever we see an x, we're going to replace it with a 4. So we have square root of 2 times 4 plus 1, which would be the square root of 9. which of course we know is equal to 3. So looking at the first example, h of 4 equals 3. 4 was the input, 3 is the output. Okay, next one is h of 0. Same thing, replace your x value with the 0. So square root of 2 times 0 plus 1, which would be the square root of 1, which we know h of 0 then is equal to 1. Okay, above exercise 2, we see this box where, again, they are talking about function notation that we began the video with. You can see y is equal to f of x. So y is equal to f of x, which is equal to our output. Our input is x. So in the second exercise, we're given the rule, the function rule, f of x equals x divided by 3 plus 7. And we're asked to first explain what the function rule does to convert the input into an output. So let's just kind of take a look at what this rule is telling us to do. Okay, remember our input is the x value. So here it's telling us to take the input and divide by 3 and then add 7. So that's what the rule is telling us to do. Take the input, divide by 3, and add 7. Okay, so now let's evaluate f of 6 and f of negative 9 using this rule. So f of 6 would equal to exactly what our rule tells us to do. Take the input, which our input is the 6, divide by 3, and add 7. So 6 divided by 3 is 2, add 7, and you get 9. So f of 6 equals 9. Okay, now let's evaluate f of negative 9. Again, follow the same rule. Replace the 9 in for x. The negative 9 is your input. So negative 9 divided by 3, add 7. So negative 9 divided by 3 is negative 3, add 7 is 4. Okay, next we're asked to do something a little bit different than we've been asked up to this point. This time we're asked to find the input. Remind me, what is the input? It's the x, for which f of x equals 13. F of x, remember, is the output, equals 13. So they're telling us that the output is 13 and they're asking us to solve for the input. So when I take this f of x equals x over 3 plus 7, I'm not replacing the x with my 13, I'm replacing f of x with 13. So 13 equals x divided by 3 plus 7. Okay, so now if I wanted to solve that for x, it's a linear equation I'm solving. I'm going to subtract 7 from both sides. So I have 6 is equal to x over 3. Now to get at x, I would do the opposite here. So I'd multiply by 3, multiply by my denominator. So 18 is equal to, here the 3's cancel, and I get x. So I solved for x, which is the input, when the output was 13. Okay, for the next example, we're reminded that function rules commonly come in one of three forms: equations, which is what we just dealt with in the first two exercises, tables, and graphs. The next exercises will illustrate functions as a table and as a graph. So the first one we're going to look at here, number 3, is looking at it as a table of values. Okay, boiling water at 212 degrees Fahrenheit is left in a room that is 65 degrees Fahrenheit and begins to cool. So what this is saying is that we have boiling water, we take it off the stovetop, we put it on the normal counter, and we just then let it sit. And then it says temperature readings are taken each hour and are given in the table below. In this scenario, the temperature T is a function of the number of hours, H. So T, temperature, is a function of the number of hours, H. So if you look here, h is our input function of the number of hours h. So h is our input, and depending upon how many hours have passed, we can read our temperature at that time. So if I'm asked to evaluate using a table, it's really pretty easy. If I'm asked to evaluate T of 2, remember 2 is my input, which in this case is my hours. So what is the temperature after 2 hours? The temperature after 2 hours is 104 degrees. Okay, what about T of 6? So same thing. 6 is again our input, which in this case is h hours. And so the temperature after 6 hours is 68 degrees. Okay, now what we're going to do, letter B is asking us to go the opposite way. For what value of h, meaning they want us to solve for the input, when T of h is equal to 76. So now they're giving me 76 is the T, that is the temperature. So now if I look on my table of values, I'm looking for the temperature of 76 and saying what number of hours, that's 4. So h equals 4 is the answer. And that's because T of 4 equals 76. So take a look. 4 is the hours that give me an output, an answer, a temperature reading of 76 degrees. But my answer here is h equals 4 hours. Okay, our last example of the night is taking a look at a graph. So the function y equals f of x is defined by the graph shown below. It is known as a piecewise linear because it is made up of straight line segments. Answer the following questions based on this graph. Don't get too bogged down in the piecewise linear made up of straight line segments. The idea here is that you can see we have a whole bunch of different line segments that kind of are all connected, one right after the other. Later in the year, much later in the year, we're actually going to talk about piecewise graphs, and we'll look a little bit more in depth about them. So here, if I'm asked to evaluate, again, I have to keep in mind my inputs and outputs. Now, on a graph, where are the inputs? Well, think about it. Your inputs are your x values. So where are my inputs? They're on the x-axis, which I'm highlighting here in green. My outputs are my y values. Those are on the y-axis, which I'm highlighting in pink. Okay, so if I am asked to evaluate f of 1, that's telling me to go to 1 on the x-axis, which is right here is a 1 on the x-axis, and go until I find a point, which is right here. What is the height or the y value of that point? And I would say it's 4. So f of 1 is equal to 4. Okay, so let's do the next one, f of 5. Again, 5 is the x value. So go to 5 on the x-axis, 1, 2, 3, 4, 5, that's right here. Here's 5 on the x-axis. Go find its coordinating point on the graph. There should only be one because it's a function. And what is the height or the y value of that? -2. Okay, f of -3. So -3, go on the x-axis, backwards 3. That's right here. Find the coordinating point. What is the height or the y value? 1, 2, 3, -4. F of 0 is, okay, the 0 on the x-axis is right here. That's our origin. And so we go up until we find that point. It's on the y-axis, but it's how high on the y-axis? It is 2 up on the y-axis. Okay, now we're going to go the other way. This time, it says solve each of the following for all values of the input x that make them true. So we start off with f of x equals 0. Remember, this is the y is equal to 0. So my y-axis is the axis in pink. Go to when y is equal to 0. Okay, that's this way here. And say how many values. If you notice, there's actually 1, 2, 3 x values for when y is equal to 0. Okay, now I'm looking left to right to get this answer. So how many x values is it? Well, -1. So x equals -1. Then this one here would be when x is equal to 1, 2, 3, 4. And also when x is equal to 7. So if I said when x is equal to -1, what is y? You would tell me 0. When x is equal to 4, what is y? And you would tell me 0. When x is equal to 7, what is y? And you would tell me 0. Okay? All right, f of x equals 2. So now I'm doing the exact same thing, but now I'm looking at 2 on the x-axis. I'm sorry, on the y-axis. So I go to 2 on the y-axis, and I want to go across. Well, one of them is the point that I was already on. So when y is 2, x is either 0, or also here, which is 1, 2, 3. So when x is 0 and when x is 3, the output is 2. Okay, the last question says, what is the largest output achieved by the function, and what x value does this occur? What is the largest output? So output, remember, are your y values. And the largest, another word for that is the maximum. So what is the maximum y value? So if I just look at my graph, I can see that my maximum, my highest y value occurs right here. Okay? And what is that? So the maximum y is equal to 4. So it occurs at y equals 4. At what x value does this occur? So go down and read the x value at that point, and I would say at x equals 1. So thank you, ladies and gentlemen, for sticking with me here tonight. I know that some of this stuff can be confusing, and you might get a little lost from time to time, but as we work through them, I think it'll become more and more natural and secondhand for you, and you'll be able to use this notation more comfortably. So we're going to practice next time in class, and hopefully getting you feeling a little bit better about using function notation to describe and evaluate functions. Thanks a lot, have a great night, and we'll see you in class.